I'm going to prove the Holder inequality. We have a bunch of positive real numbers, and we have the following inequality. So a times a1 times b1 plus a2 times b2 plus all the way up to an times bn is no larger than the product of the 1 over p, the pth root of the sum from 1 to n of ai to the power of p times the sum from 1 to n of bi to the power of q. Take the qth root. Of course, p and q are both larger than 1, and 1 over p plus 1 over q is equal to 1. That's the condition, the Holder inequality. So equal sign holds if and only if for every ai to the power of p is equal to some constant lambda times bi to the power of q. So for every ai to the power of p, bi to the power of q are proportional. And of course, first we have to prove the Young inequality. So this is one of the many other different ways. So it says that if we have a function phi, if it's monotonically increasing and it's continuous over this interval, and if phi of 0 is equal to 0, and of course we have to restrict a and b between 0 and some, for example, b is less than phi of, I'll explain why. I'll explain the meaning of this. So then we have a times b is no larger than the integral from 0 to a, phi of x dx plus the integral from 0 to b of the inverse of phi of y dy, the sum of two different integrals. And so the equal sign holds if and only if b is equal to phi of a. So we can just draw a graph and simply see what's going on. So for example, we have a monotonically increasing. Of course, I'm just going to skip the rigorous proof, right, because it's easy to verify. So just roughly from the graph, x, y, 0, say it's monotonically increasing. Right, maybe let's draw a graph looks like this. Right. Of course, it may look like that. Right? So this is a convex function. It may be a concave function as well. So the reason I want to, for example, I have a. So a is larger than 0. So phi of 0 is equal to 0. So since it's monotonically increasing, of course there is a inverse function exists. Right? So inverse function like this. So if we just draw some other point b, so b is here, also larger than 0. Let's say if b intersects with the graph somewhere here. So what's a times b? Right? A times b is the area of this rectangle, of this rectangle. Right, so it's this area. Right. So of course, this area of the rectangle is a little bit smaller than the area of the area under this curve plus the area under that curve. Right? The reason is because we have the area of this bit, right? So the area of this little bit is what makes the right-hand side a little bigger than the left-hand side, right? So this. So the reason I want to say b is less than phi of positive infinity is I consider the situation where we have the asymptote. For example, maybe the graph will look something like concave function, right? Maybe it'll increase like that. Maybe it'll have asymptote, right? Asymptote. So maybe asymptote line is here. So I want to restrict b to be less than the asymptote value, right? So that b can actually intersect with the graph somewhere here, right? So this is b. and maybe A is somewhere here, right? So again, the AB represents the area of this rectangle. Right? Of course, it will be smaller than the area of under this curve plus the area under that curve. That is the area of this, right? So again, it's because we have this little bit extra area that makes the right-hand side bigger than the left-hand side, right? I'll just skip over the rigorous proof because it's easy to verify. So just from the graph, it's easily verifiable. So equal sign holds if and only if B equals phi of A, right? So equal sign holds if and only if we have, for example, if we have A somewhere down here, and if we have B instead of being here or there, we say B is sitting at this point, right? So exactly sitting here. That's where B is. In other words, in this case, if B happens to be equal to the functional value at A, right, of phi, then we have the area of the rectangle AB is equal to exactly the area under this curve and the area under this curve. That's the inverse function curve, right? So under this curve, exactly equal to each other, right? So also it's easily so we're done with this. We're done with the Young inequality. So we're going to construct a function, let's say function phi of x to the power of p minus 1. Right? So we just assume p is bigger than 1. So that the power is positive. Right? A positive power of x, its graph is, of course, monotonically increasing. Right? Also, it's convex function. Right? It'll look like something like this. Of course, it'll have a inverse function. Also, it is continuous. Right? Continuous, monotonically increasing. Inverse function exists. So we're all good. And so I'm going to choose A and B constant bigger than 0. Of course, there is no asymptote whatsoever, right? So we're fine. Don't have to worry about that. So in this case, I can say that Young inequality, right? According to Young inequality, I have A times B is, of course, I have to calculate the inverse function, right? So y equal to x to the power of p minus 1. Inverse function, y to the power of 1 over p minus 1 is equal to x to the power of 1. Right? So in other words, phi inverse of, right? So now this is my, so y. So y appears here. So in other words, inverse of y is equal to y to the power of 1 over p minus 1. Right? Inverse function, right? Which projects to the value of x. Right? This x. Right, so originally we have maybe x and y. So originally we have this projection, right? Called x to the power of p minus 1. Right? Inverse we have, we plug y into our function, we have y to the power of 1 over p minus 1. Right? Inverse projection. So now my Young inequality tells us that a times b is less than or equal to the integral from 0 to a of phi of x to the power of p minus 1 dx plus integral from 0 to b phi inverse this one. Right? So y to the power of, I'm just going to make some notation and say, let's just say 1 over p minus 1 is equal to, let's just call that q minus 1. Q minus 1. Right? So let's solve for q. So in other words, q is equal to 1 over p minus plus q, p minus 1. Right, p minus 1 plus 1 plus q, p. Right, p over p minus 1. Let's calculate 1 over p plus 1 over q. Like I said, p is greater than 1. So that is equal to what? So 1 over p plus 1 over q. Q is equal to this. So in other words, 1 over q is equal to just p minus 1 over p. Right? P minus 1 over p. So what is that equal to? P over p equal to 1. Right? So condition is satisfied. Right? So yes. So this condition is satisfied. So we're going to use that. So now I can say that y to the power of 1 over p minus 1 is equal to, like I said, q minus 1. So q minus 1 dy. Right, dy. So now I can say that a times b is no larger than the antiderivative p, x to the power of p, evaluated from 0 to a, plus likewise q, y to the power of q, evaluated from 0 to b. The same thing, similar. So ab is less than or equal to p, x, a to the power of p, right, 0, nothing, right, plus q, b to the power of q. Right, this is what I have. So equal sign holds if and only if b is equal to phi a, right? So holds if and only if b equal to phi a, b equal to phi a, what's phi a? Phi a to the power of p minus 1. Right, that's when equal sign holds. So in other words, if we raise to the power of p on both sides, right? So in other words, b to the power of p, q equal a to the power of q times p minus 1. Right? So in other words, when b to the power of q equal the a to the power, like I said, what is q? Q is equal to p over p minus 1, right? P over p minus 1 times p minus 1, right? So they just cancel out, equal to a to the power of p. All right, so that's when equal sign holds. I've just copied down the progress so far. So I've established a function phi of x to the power of p minus 1, and successfully worked out its inverse function, y to the power of q minus 1, where p and q are both bigger than 1, and 1 over p plus 1 over q is equal to 1. And given that a and b are both positive, according to Young inequality, we have a times b is less than or equal to a to the power of p over p plus b to the power of q over q. Equal sign holds if and only if a to the power of p equals b to the power of q. So this is what we have so far. So I'm going to utilize this fact to calculate to prove the Holder inequality. So how can we relate AI, BI, right, to our results? So in fact, let me just denote, because this is too long, let me just denote A is equal to the sum from I, so from 1 to n, AI to the p, power of 1 over p, this is A. B is equal to sum from 1 to n, bi to the power of q, to the power of 1 over q. Right, this is B. So in fact, if I fix any positive integer I, right? Any I, once given, we fix it. Now, then I have, if I let A equal to, for example, so I'm using the number in here, A1, A2. I'm choosing some fixed AI from here. Right? So AI over, I'm going to use this number, right? This is, notice this is already a fixed number, already a constant, because this summation already completed, right? So over A. Right? Also, I'm going to let B equal, likewise, BI over B. So according to the fact we established, right, A times B, that is AI, BI, right, over A times B. It's less than, we're getting very close to this result, right? AI, BI, right? But we're still missing something, right? Still, so less than or equal to this, right? So A to the power of P over Q. What is A to the power of P? A to the power of P is this one, this guy to the power of P, right? So I have 1 over P, right? That's P, 1 over P. So A to the power of P, that is times AI to the power of P over capital A to the power of P. Right, distribute the power. And plus, likewise, 1 over Q times B to the Q. Right, B to the power of Q. That is BI to the power of Q over B to the power of Q. Right, this is what I have. And also, notice that A to the power of P, like I said, A is equal to this sum to the power of 1 over P, right? So in other words, A to the power of P, right? P and 1 over P cancel out. I have sigma sum from I to P, right? And also, likewise, B to the power of Q, for the same reason, is equal to sum from 1 to n of BI to the Q, right? So since this inequality is true for any fixed positive integer I, then I can do summation on both sides, right? Sum from 1 to n still holds true, right? Still holds true. So sum. So since A and B are already constants, right? Already constants, I can just take them out. So that is A times B, right? Under sigma sum from 1 to n of AI, BI, AI, BI, right? Less than or equal to sum, right? I can distribute the sum to each of them, right? Also, 1 over p is a constant, so is a to the power of p, so is 1 over q, so is b to the power of q, right? I can just take them all out. So in the end, I have 1 over p times 1 over a to the power of p times sigma from 1 to n of ai to the p, right? Plus, likewise, 1 over q, right, times 1 over b to the q times sigma from 1 to n of bi to the q, right, bi to the q. Right, this is what I have. So remember, I've just shown that since a is equal to this, right? I've shown a to the power of p is equal to the sum of this, right? So sum, right? This sum, that is this sum, right? So this sum actually, a to the power of p, right? Is it, right? A to the power of p, and this sum, b to the power of q, right? So I have 1 over a to the power of p, and I have a to the power of p. They just cancel out, right? Likewise, 1 over b to the power of q and b to the power of q, they just cancel out. And I still have 1 over q plus 1 plus p, so in the end, 1 over p plus 1 over q is equal to 1, it turns out, right? I've shown previously, right? Because I denoted it, whatever. So this fact I established previously, right? So that is definitely true. So right-hand side becomes 1 all of a sudden, right? So I multiply AB over, right? I have sigma from 1 to n, AI, BI is somehow less than or equal to just A times B already, right? So A times B is sigma to the power 1 over P, right? B is this, so this is what I have on the left-hand side, right? And this is what I have. This is A, right? This is A. Right? B is this. That is exactly this. And so when does equal sign holds in this case, right? So, like I said, we've established equal sign holds if and only if A to the P is equal to B to the Q. So we've denoted A equal to AI over A, right? For every I. So this raised to the power of P is equal to that raised to the power of Q, right? So equal sign holds if and only if AI for every AI to the power of P over A to the power of P. Capital A to the power of P, right? Capital A to the power of P, right? This is gone, so sigma, this sum. So don't worry about this sum. This sum is whatever. It's already constant, right? Is equal to B to the Q, right? This to the power of Q. Right, see, sum. This sum, right? Different sum than this, but still a constant, don't worry. Bi to the power of Q. Okay. So in other words, I have this multiply over to there, constant over constant, still a constant, right? So still I have AI to the power of P is equal to some constant times Bi to the power of Q. Right? So, like I said, really, equal sign holds if and only if, every ai to the power of p and bi to the power of q are proportional.